Friction is our next topic, and there's one weird thing about friction compared to everything else. Uh, but before we get into that, keep in mind that what we're trying to do with physics is model nature. We want to be able to predict what happens and explain what we observe. And what's actually happening with friction is we have two surfaces in contact, and even if they feel perfectly smooth to you, if you looked on the microscopic level, you would see there are hills and valleys. And as we drag one object across another or try to move one object off of another, those hills and valleys are bumping into each other and binding atomically, and it ends up it would be an impossible mess to try and predict what the friction would be from first principles, where we look at the surface and try and figure out how much binding there's going to be. Nobody does that. We will be able to measure it, which is easy enough, and talk about it experimentally, which will be good enough for what we're concerned with. And there's two kinds of friction. We're going to start off with static friction. That's when something is sitting still and we want to move it. If it's already moving, the force of friction on it is known as kinetic friction, and that's a little bit different, but we'll treat that later too. As it turns out, the weight of the object is not the important thing when we look at friction. It's actually the normal force, because that's what describes the force between the surface of contact of the object and the floor or the table or whatever it's sitting on. So there's the normal force, and then there's also a material-dependent constant that describes how sticky the surface between the two materials is. So for example, if we were talking about a piece of rubber and a piece of metal, we'd probably have a pretty high value of coefficient of friction between those. But Teflon and an ice cube, we'd have a very, very low coefficient of friction there. And we'll see that there's one for static friction, mu s, and then there's a different one that's lower, mu k, for kinetic friction. So to start off, let's say we have a 100-kilogram block sitting on carpet. We try and push it to move, and we apply 100 newtons and it doesn't move. We apply 200 newtons and it doesn't move. We start to gradually apply more and more force, and then when we reach something like 283 newtons, it just starts moving. What that tells us is the maximum static frictional force here is 283 newtons. We'll call that Fs max. And we have a formula for this, which is just mu s times n. Notice that mu s has to have no units, since n is a force, and this frictional force is also a force. Here's the part that's a little bit crazy and starts to confuse people. When you were applying 200 newtons, what was the static frictional force? People are very tempted to say 283 newtons, the maximum. But if that had been the case, notice that when you do the math, you find that the object would have started chasing you. You push it, and if you're not strong enough to move it to the right, it starts moving to the left. And that doesn't match with reality. So what we really have for static frictional force is an inequality rather than an equality, like pretty much everything else you've dealt with. Only if we're talking about Fs max do we have a regular equality. So we can relate these things like this. The static frictional force is always less than or equal to Fs max, and Fs max is exactly equal to mu s times n. Now, that you would catch the mistake you make in the case above if you put in 283 and you noticed, hey, wait, this thing is moving backwards. But in some cases, you might not notice it. And the most common problem, the biggest mistake people make when they're doing static friction problems, is they just assume that the frictional force is always Fs max, which is mu s times n, all the time. In a case like this one below, where we have the mass on the inclined plane and the mass hanging from it, just from looking at that, unless you're incredibly good at physics and doing math in your head, you really have no sense of which way this should be going. So for example, if I turn friction off, will the block slide down the plane or up the plane? So in that case, if you did this and just included Fs max as another force, you'd have to pick a direction for it to go first. And once you did that, you might not know that you have a crazy result, because this block could move up the plane or down the plane, and it wouldn't really be surprising either way. So what we have to do to handle this and avoid making this mistake, first we work the problem without friction and find the sum of the forces along the direction of motion. So this would be along the plane. Then we calculate Fs max. Now remember, this is a regular old equality. We can calculate this without worrying about anything. Then we compare them. If the sum of the forces trying to move it is less than Fs max, the object won't move. In that case, the actual frictional force just matches the other forces. So in the case above, when you were applying 200 newtons, the object you were trying to move was also applying 200 newtons the other direction. On the other hand, if the sum of the forces is greater than Fs max, then we can treat friction like just another regular force. Sum of the forces minus Fs max is ma. So first we do this for a block on an inclined plane. Notice we haven't drawn in the frictional vector yet because we're going to do this without friction first, and we've done this one before. So picking the axes along the plane and perpendicular to the plane, we get in the y direction, sum of the forces is may. That's going to be 0 experimentally. So again, we get n equals mg cosine theta. We've found this several times before, but this is the first time it'll be useful for us. In the x direction, we have negative mg sine theta equals max. Now, ordinarily, what you would do is divide out the mass and find that acceleration, but we're going to stop a step before that because what we really want is just sum of the forces. So this is far enough. Now, the real free body diagram, we're going to have friction acting up the plane. Notice that if we were doing this on this example, we would have to pick a direction for Fs to act, and we might very well get that direction wrong. So we'd have to be prepared to go back and flip it around. Anyway, here we know that the friction will act up the plane. And what we want to find here, our second step in this process, is find Fs max. So that's mu s times n, and now we finally get some use out of that Newton's second law equation that gave us n equals mg cosine theta. Now we can plug it in here, so we get Fs max is mu s mg cosine theta. Now we can put in some numbers. If we say mu s is 0.25, it's a 7 kilogram mass, and the plane is at a 30-degree angle to the horizontal, we calculate Fs max very quickly and get 14.85 newtons. Then we compare that to the forces acting on the mass, trying to move it. This is just negative mg sine theta like we found before. We calculate that, it's negative 34.3 newtons. Now when we compare these two things, we're comparing absolute values. They're obviously going to go in different directions. So what we get is the applied force is greater than Fs max, so this block will slide down the plane. Now what if we'd had a different result? What if the plane is much stickier? Let's say mu s is 0.75 instead of 0.25. We don't have to redo anything except the Fs max calculation. When we do that, we recalculate, we get 44.56 newtons. This is larger than the applied force, so this block is not going to move. And the actual frictional force in this case is just the negative of the applied force, negative 44.56 newtons. Once we've gone over Fs max, then we've got to go back to kinetic friction. That's something simple again. But it's simpler than static friction. We still have to use this, but we don't ever assume that we're going to be using this unless we're told the block or whatever is already moving. For an example involving kinetic friction, we can start off with our formula. Fk is mu k times n. We notice this will always be, the mu k will always be less than mu s, and this is just a reflection of the experimental fact that it's easier to keep something moving than to get it moving in the first place. Let's say we take a block and slide it down an inclined plane, and we're given these parameters, 20 degrees and mu k is 0.1, with an initial velocity of 10 meters per second. Does it gain speed or lose speed as it travels? We have the same free body diagram, only now it's Fk pointing up instead of Fs. Now, one thing to keep in mind, the initial velocity of 10 meters per second, we don't care about that at all for purposes of calculating the force, except for the fact that it tells us we'll be working with kinetic friction rather than static friction. Other than that, remember that the velocity has no place in any of this until we've solved the problem and then see if there's a kinematic equation question at the end. So, we have the same thing in the y direction. We again get n equals mg cosine theta. What we now have in the x direction, though, we have Fk pointing up the plane, positive, and mg sine theta pointing down the plane. And their difference gives us max. Since we don't have to do anything crazy for fk, we just plug in mu k times n. We can rewrite this mu k times n minus mg sine theta is max. And we know the normal force, we plug it in. Now we can cancel the mass, and we find that the acceleration is mu k cosine theta minus sine theta, that whole thing times g. And that gives us negative 2.43 meters per second squared. The fact that this is negative, that means the block is accelerating to the left, which is down the plane. So in other words, it's going to keep gaining speed because gravity is stronger than friction in this case. And now we could ask questions like how fast will the block be moving in 2 seconds, how long does it take to slide 3 meters, all that kind of stuff. And we have what we need. We have AX, and then for those questions we have V initial is 10 meters per second. This is the only time we care about it if we're asked some kind of question like that. If all we were asked is the acceleration, we wouldn't care. Now, if we change that coefficient of kinetic friction to 0.5 instead of 0.1, so we make it a stickier surface, we don't have to redo everything. We can just go back to this and plug in the new value. And this time we get plus 1.25 meters per second squared. So now the block is accelerating to the right, which means it will slow down and stop if the plane is long enough. So again, we could ask a bunch of kinematic questions like how long does a plane have to be for this to stop? How much time does that take? Things like that. And that's the only place where we care about that.